Hi all, this is Dr. Huckaba. This lecture is part of a lecture I had from earlier in the semester where we were talking a little more in depth about molecular orbitals, specifically frontier molecular orbital theory and how those orbitals mix to make bonding or anti-bonding patterns. Additionally, there's a little more too about bond line drawings and how you can calculate formal charge. So enjoy and thank you. But before we leave, or you get to the lecture, here is your to-do list for today. First, obtain access to Gradescope. Hopefully you've done that. Do your homework assignment 1, which is due August 21st. Start working the Chapter 1 problems while also beginning to read Chapter 2. As always, if you're in need of anything, contact me. That includes if you have an academic conflict or need or have a letter of accommodation. Thanks and enjoy. Imagine that we are mixing a p electron and an sp2 electron from the same atom with another atom that has a p atom and an sp2 atom. 1. In your head, on a paper, whatever, can you imagine what each of those p and sp2 orbitals looks like? Okay, I'll give you a second so you can do that. Okay, maybe we're looking at 2 carbons coming together. Why did that happen? Oh, yeah. So, okay. Now I'm opening it up on my computer, so I'm with you guys. Okay, great. Next, if you mix each of those orbitals together, 2 from one side, 2 from another, 4 in total, can you imagine in your head, on a piece of paper, what the mixed hybridized orbitals will look like? You start out with the first bond, which is sigma on bottom and sigma star on top. Okay, do you guys remember sort of what a sigma and sigma bond, or what a sigma bond looks like to begin with? Yeah, it looks like 2 atoms. Well, here we'll choose carbons. This is 2 atoms with a single bond. Maybe also you can imagine a sigma bond looks like 2 hydrogens, or perhaps a carbon-hydrogen bond. And the reason why it's called a sigma bond is because that's a formalism, meaning that this is kind of 2 s electrons coming together, and the bond is more or less a sphere in nature. Okay. Next, wrong one. There we go. And the structures are what you can see here, where the bonding interaction is fully shared between the 2 atoms, and the anti-bonding interaction is not shared at all, meaning that there is no electron density in between those 2. And essentially, if there's no electron density between 2 atoms, that means there is no bond. Does that make sense? Anybody? Shaking your head, nodding your head? Okay. That means there's no bond, and that is the reason why the sigma star is so high in energy. Because if you promote an electron out to that energy level, you've just broken the bond, essentially. You know, that's an anti-bonding interaction. Okay, so these are the 2 sp2 orbitals that have come together to make a bond. What about the p orbitals, right? So if we're talking about maybe ending up with a doubly bound set of carbons, what do those atoms look like? Do you remember perhaps from, or those orbitals? Do you remember maybe from last lecture where you have 2 mixed orbitals? In this case, the formalism is you have 2 p orbitals mixing, you make the Greek letter pi. Okay? You can have a pi and a pi star just like you can have a sigma and a sigma star. And essentially, just like we saw for the sigma and sigma star interaction, one has a bonding interaction, one does not. The pi bonding interaction looks like 2 clouds of the same phase over the carbon on one side and the same on the bottom. In this drawing, they've put them together to form 1 cloud on top. And that's because you can't really say for sure where the electrons are. They're somewhere there in the middle, so for ease of formality, we put them there on top and bottom. The antibonding interaction, you see the exact same thing. There's actually no electron density shared between those atoms, meaning that if an electron is promoted from the pi to the pi star, you will have a very weird situation, but also the chemistry should be different because now those electron, that electron that you put into the higher energy orbital has a different spatial arrangement, right? So maybe it will do things differently than the pi orbital did. And if we fill them from the sp2s, you can see that we have 2 electrons. It fills the bottom sigma orbital, and the same with the p orbitals, making the pi. And you're left with one highest occupied molecular orbital, which is the pi in this case, and an lowest unoccupied molecular orbital, the LUMO, which is the pi star. I think if you've looked at the homework, maybe seeing some of these Greek symbols will make sense to you, and hopefully you will see this and have a little direction as to how to answer the question in the future if you haven't tried the homework at all. All right, so with that, I think it is time to start lecturing on organic chemistry for real. Do I have any questions from anybody before we start? Chemistry, non-chemistry? No? Okay, cool. So where we left off last time was in bond line diagrams, right? We were talking about communication in organic chemistry and talking about taking some of the tediousness out of drawing structures. So let's start with the structure that we had talked about at the very end of last week's lecture, and that is this one. Okay, maybe you all remember that. So in case you don't remember, lone pairs don't have to be drawn. I did in this case. So we'll draw those to start out with in a line bond diagram or line bond structure. Additionally, CH bonds are never drawn, so you have to remember they're there. Sometimes, if it's an important question or I'm trying to keep everything straight, I'll just go ahead and write the formula out. So in this case, it's it's C1, 2, 3, 4, C4, H3, 5, 8, 11, N. Right? So that way you can look at that, you can say, did I have it right, did I have it wrong? And you can know if you need to be thinking about charges or not. Now, this might look just as dumb as the partially condensed structures to you, and that's okay. Because it's only when you really see how bad structures can get as they get bigger that you really truly appreciate why bond line drawings are important. Okay? And if you saw just how complex a partially condensed structure, like on the left, can get with a fairly simple molecule, aspartame, the bond line structure is on the right in this case, you can start to really appreciate it. Because very quickly you've communicated connectivity between atoms, a little bit of stereochemistry, which we'll talk about in chapter 5 or something, which is the wedged bonds coming out. And you don't have to worry about all those hydrogens. So we are working towards a way to communicate complex structures easily, but for now it probably will feel a little painful to get used to. So we'll all walk through this together and hopefully all become comfortable with it soon. Okay. Now, with bond line structures, you remember certain things like carbon always has 4 bonds, right? Just like we've been drawing them. Carbon always has 4 bonds. If your carbon has 5 bonds, something is wrong. Go back and draw it again. Carbon never, ever, ever has 5 bonds. I missed lots of questions in this class when I was a student because carbon has 4 bonds. Okay, 4 bonds. You can also use bond line structures to communicate double bonds as well, and triple bonds. For instance, let's say you have hexane, okay? Hexane, 1, 2, 3, 4, 5, 6. Hexane is C6, H3, 5, 7, 9, 11, 14. And it's fairly simple to communicate something like hexane. Similarly, let's say you have a double bond in the 1 position, and you want to draw hexene. Okay, that's like this. 1, 2, 3, 4, 5, 6 carbons. So we got the hex part right. H3, 5, 7, 9, 10, 12. Does everybody see where the 12 came from? Just a shake of the head will be enough to tell me if you didn't see where it came from. Okay, I'm seeing some nods, I'm seeing some shakes. It's totally fine. This is the first time we are looking at these things. All CH bonds are implicit in these. So you have to remember, carbon has 4 bonds, as I said a couple times. And if you have a double bond, that means you replace one of the CHs that is implicit with that double bond. So in this case, you only have 2 hydrogens on the one side and 1 on this internal side. Whereas in the hexane portion of the molecule here, you see that there are actually 5 hydrogens in that same area. Okay, so you have to imagine that the hydrogens are there, or do like I'm doing each time and go through and make sure you're accounting for all the implicit hydrogens that you're trying to look at. Okay, alkynes do the same thing. They look a little funnier, but they do the same thing. So if you have 1 hexyne, meaning that the first carbon with a triple bond is the first one, it looks like this. 1, 2, 3, 4, 5, 6. Okay, do you see that there are 1, 2, 3, 4, 5, 6 carbons here, just like before? But this time there are 3, 5, 7, 9, 10 hydrogens. Okay, who is seeing that? Anybody not seeing that? You can shake your head. No judgment, we're all learning. Okay, I'm not seeing any head shakes. For the same reason that there are 3 implicit hydrogens here, and in the double bond, there's only 1 implicit hydrogen in the alkyne version. And that is because each of these carbons has what? 4 bonds, that's right. They all have 4 bonds. 4 bonds here, 4 bonds here, 4 on each. Always remember, this implicit, explicit stuff gets a lot easier if you remember carbon has 4 bonds. Okay? I will draw every single time all carbon-carbon bonds to make it easier. I'm not making it easier on you. It is easier because all of the carbon-carbon and carbon heteroatom bonds are there for you. The rest of it is just accounting for hydrogens. And it may seem stupid that I'm spending so much time on this, but I promise you, you get into a test and sometimes you question everything. So having this to fall back on is really good. Now, you notice that I'm drawing these all in kind of the same way. I'm kind of going, in these 90-degree up-down motions. And that's because these are often the ways that we not only depict organic chemistry, but if you remember from last lecture, when I was drawing the bond line structures with the dashes and the wedges, there was always these 2 here that looked kind of more 90 degrees. We know from earlier that they're actually 109.5. Is that right? Yeah, 109.5. But it's harder to get that exactly when you're drawing these bond line diagrams. So if you just imagine drawing 90 degrees angles each time, then you'll be okay. And you can draw lots of organic molecules this way. Here, this aspartame molecule, you can see they do a similar up-down motion. and they always put the carbonyl in a vertex. And whatever you start with the carbonyl, the double bonded oxygen, you come down the next time. Okay? You don't draw something like this. That doesn't make sense. And it doesn't make sense because sp2 hybridization means we have 120 degrees, right? We all remember that bit from last week? Or this week? Was it just Tuesday? I guess it might have been. It's been a long week, man. This is not 120 degrees, right? This is much less than 90. So try to remember about hybridization as you draw, and it will help your structures not only look better, but be easier to be communicated as well. And one of my favorite things about bond line drawings, besides taking something monstrous like aspartame and making it easier to read, is that you can actually communicate reactions much better as well. So far, we haven't talked about reactions at all. In Gen Chem, maybe you talked about it a little bit, right? You had some acid-base reactions happening or some precipitation reactions. And they generally, if I'm remembering right, look something like this, right? Where you have some formula, and then you do something to it. In this case, have hydrogen and some platinum, and then you have, I don't know, some other formula, right? That's generally Gen Chem, because you were studying some basic principle of chemistry. You didn't really care what that was, but you saw that a change happened. Okay, that was a Gen Chem style reaction. In organic chemistry, with bond line drawings, you see something totally different come out. Okay, this is the big thing about organic chemistry, is that you can actually account for what change happened based on what you add to your chemicals. Okay, so what this means is, this is your first lesson in how to speak OChem. Well, I guess your second lesson. Your first was up on the board already. Left side of the reaction, those are your reactants. Okay? In the middle, you have this double barbed arrow. Above it go your reagents, anything you add to it. The bottom is your things like your catalyst, maybe if you have one. In this case, it's platinum. And in this way, you can talk about reactions that might happen to aspartame or other similarly complex molecules fairly easy, because all you have to do is see what functional groups were changed in the reaction. That's right, a functional group. Has anybody heard of a functional group before? Couple raised hands. Okay, there's no problem if you haven't. Perhaps what separates organic chemistry from all others is functional groups. Okay? These are patterns of both reactivity and connectivity that cause different types of chemistry to happen. Okay? This is what makes lots of special chemistries very interesting. And there's a ton of different functional groups. Okay? Up here on the slide, you'll see, I don't know, 20, something like that, functional groups. I think I saw somebody on Twitter say that there were like 600 that they could name, and it was just some person going through and naming all they could. These are distinct types of distinct patterns that have their own intrinsic properties. Okay, you can look at an alcohol, as we did before in our last class with our thinking outside the box question. You can look at an alcohol, no matter what that group is connected to, and make some assumptions. You can you can reason by analogy about what that molecule might do. Okay, the same way with amides. Here, I don't know if you can see that. Yeah, amides. And the same with carboxylic acids, with ketones. All of these things you can use reasoning by analogy once you're familiar with these functional groups. Yeah, it's the reason why you know why a molecule like morphine does its job. Because you not only have the functional group that does something, you can see amines, ethers, and phenols, but also they take up different amounts of space. You know, we talked about these VSEPR types of qualitative analyses, right? You saw geometries. That really comes through in molecules. And especially if you're looking at biological systems, these can have a huge impact on what the molecules do. You know, morphine has a big stigma to it right now. Penicillin is one of the most important molecules of the 20th century and is so important because of its shape and the functional groups that it has. And it would only have its shape and only act like it does because it has these specific functional groups. So we're taking a turn in this class. We are moving away from talking about how to effectively communicate chemistry, and we're going to start talking about how to draw molecules, how to really accurately represent their functional groups so that we can understand their reactivities. I think if you really pay attention to this next section of the lecture, it will make your lives very easy as you learn more about electron pushing and resonance structures. Because functional groups, as you may realize, never change. Okay? This penicillin here, this part of the molecule I'm mousing over, it's made of an amide. This beta-lactam here is made of an amide that is bound also in a cyclobutane ring. Okay, and here in the 3D structure, you can make out the amide and the cyclobutane ring. And if you go structure to structure and see similar cyclobutane rings with an amide, you will just about always know what they're there for and what they're doing, if you understand that particular functional group. So we are going to, that's obviously the big picture. That's supposed to bring you in here with me, and we're all supposed to now know where we're going, okay? But the unfortunate thing is we're going from some big picture, nice, motivating thing, so now we really need to come down and draw these structures and understand them, push some electrons together.